lab lecture. So today we're looking at sequence B, which is the synthesis of nylon. So nylon is prepared commercially via pyrolysis of adipic acid and 1,6-hexane diamine to prepare polymeric nylon. The nylon polymer that we're preparing is known as nylon 6,6 because we have a 6-carbon adipic acid, dicarboxylic acid, and a 6-carbon hexane diamine. The industrial process to prepare nylon typically prepares nylon polymers with a monomer count of in the ballpark range of 400. Of course, there's some variance in the polymer length, but this repeating diamide pattern forms the backbone of your nylon polymer chain. So this is a classic amide formation reaction. And what we're going to be doing in this lab, rather than directly reacting adipic acid and hexane diamine, is we're going to prepare adipic acid, convert adipic acid to adipoyl chloride, and then prepare our nylon polymer via an aminolysis reaction. So what we're first going to talk about is the mechanism for oxidation of cyclohexanol to adipic acid. Now, you'd think you can draw this as just a simple SN1 reaction, and I would cross out this idea. The way that I think of nitric acid, if you look at the structure for nitric acid is what is known as an oxidizing acid. So it can be thought of very similar in terms of reactivity profile to, for example, chromium trioxide. So in this reaction, we're going to be oxidizing up our substrate and reducing nitric acid to nitrous acid and nitrite equivalents. So yeah, this is sort of an incorrect proposal. So the more accurate mechanism for this reaction involves first protonation of nitric acid and generation of this nitrinium ion. This nitrinium ion is a strong electrophile, and this reacts with nucleophiles such as alcohols, and in turn we incorporate and we nitrate our alcohol. From here, after a proton transfer step, we can oxidize our alcohol to the ketone and reduce nitric acid to nitrous acid via an intramolecular proton transfer, where we pull off an equivalent of hydride and we reduce nitric acid to nitrous acid. Does this intramolecular step look familiar to anyone? Just to spark your memory, this step is closely reminiscent of the key step for the Des-Martin pyridine oxidation. It's almost identical, in fact, right? We're abstracting a hydride equivalent, oxidizing up our alcohol, and reducing our central atom, which in this case is nitrogen. Okay, now that we have cyclohexanone, nitrous acid is not just a byproduct. It actually reacts further with acid. It's protonated, and we lose water to make the nitronium ion, which is another electrophile. Now, this electrophile can't react directly with our ketone, but we can prepare a reactive enol equivalent, right? Ketones under acidic conditions can tautomerize to the enol form with a series of proton transfers. We've seen that before. From here, now that we have this enol and we have this electrophilic nitronium ion, they can react via textbook enol electrophilic substitution reaction, and that generates the following nitroso compound. Now, just like before, we can tautomerize this nitroso compound So I'd like you to think of this nitroso compound as a parallel to, for example, a carbonyl compound. And just like any typical carbonyl compound, we can tautomerize the carbonyl compound to the corresponding enol tautomer, right? Likewise, we can tautomerize this nitroso compound to this hydroxylamine-like compound. Whoops, one moment, let me adjust that. Okay, so tautomerization gives the following imine. And just like any other imine functionality, we can protonate this imine and hydrolyze this imine to generate the diketone. Does that idea make sense? So just to walk us through where we've been so far. So we make a nitronium ion that reacts with our alcohol. From here, we can abstract an equivalent of hydride and reduce nitric acid to nitrous acid. That gives us our ketone, cyclohexanone. From here, cyclohexanone can react with acid to tautomerize to the enol form. That enol form reacts with the nitronium ion to make this following nitroso compound. From here, this nitroso compound can be tautomerized to the imine-like tautomer. And from here, we can hydrolyze this imine sequentially to give the corresponding diketone. Okay, so now that we're at the diketone, we're almost ready for the key step. Is everyone following along with me so far? Okay, now, once we have this diketone, I'd like us to remember, does everyone remember how when we oxidize, for example, an aldehyde to a carboxylic acid, right? In order to oxidize up that aldehyde, we typically go through a hydrate, right? So similarly, from this diketone, we're going to form a hydrate. Now, once we have this hydrate has a nucleophilic alcohol, which can then attack electrophiles, such as the nitrinium ion. We have now generated another nitric acid adduct. Okay, now I know this part looks a little bit weird, but let's think about for a moment what's going to happen for this next step. So we have a carbonyl, and this carbonyl is pretty electrophilic. So we can attack this carbonyl with nucleophiles such as water to make another tetrahedral intermediate. Now, this is where things get interesting. When this tetrahedral intermediate collapses, rather than losing water, instead we break the carbon-carbon bond and we lose an equivalent of nitrous acid. This is how we generate the desired dicarboxylic acid in adipic acid. After a proton transfer step, we get the desired dicarboxylic acid. I know the lab manual sometimes doesn't they sometimes skip over some of these steps. So I tried to write out all of these steps as clearly as I could, referencing reactions that we've seen previously in the course. Sure, I'd be happy to zoom out, though it's quite a long mechanism. Okay, there we go. So just to give everyone the sort of the summary of this mechanism once again, as it's important that we understand what's going on. We nitrate our alcohol. We oxidize our alcohol to the ketone. The ketone tautomerizes to the enol form, and it reacts with the nitronium ion. Finally, we protonate and we engage in a series of proton transfers to isomerize this nitroso compound to this imine-like functionality, which can then be hydrolyzed with water. From here, we have this diketone, which can then be hydrated under acidic conditions. We now have a free alcohol functionality that can react with electrophiles to generate this nitric acid adduct. This is a great leaving group, and we've now primed this alcohol for further oxidation. From here, we generate a second hydrate, and this time when our hydrate collapses, we don't lose water, and we instead break our carbon-carbon bond and oxidize this alcohol further to the carboxylic acid oxidation state. And the beautiful thing about this reaction is for cyclohexanol in particular, this reaction is quite selective. So we don't have to worry as much with many of the side reactions that we typically see. These nitric acid oxidations are usually quite messy, but for cyclohexanol, the conditions have been refined as such to selectively give the desired product. I would comment as well, unless you're sure that the alcohol will properly degrade, you generally don't want to react alcohols with nitric acid under acidic conditions, because the nitrated alcohols are typically quite reactive and can usually be shock and heat sensitive. So this is a particularly well optimized reaction. Now, one thing that I would also like to comment on is that this reaction is quite exothermic and requires elevated temperatures in order to proceed. So operationally, you'll notice the majority of the recording, in fact, and I cut out like about half an hour of me adding the cyclohexanol just so that way the recording was as to the point as possible. We're adding the cyclohexanol very slowly, because if the temperature gets out of hand, we can end up with a runaway reaction and then the sample will escape from the flask. So in the lab, you're often adding it very, very slowly and closely monitoring the reaction. You'll notice from the recording, when I add a drop of cyclohexanol, the mixture immediately starts to vigorously bubble. So once we have generated our adipic acid after reaction with cyclohexanol and concentrated nitric acid, our solvent is nitric acid, and the adipic acid is not soluble in nitric acid at low temperatures. So we're going to purify and isolate our product via crystallization followed by filtration. And we're going to purify our crude product, this is our purification step, via rinsing with ice water. That will remove the off yellow color of the nitric acid and any related impurities, and we'll be left with adipic acid in water. Now, because the next step entails using thionyl chloride, We need to dry the adipic acid in the oven. I've seen in the lab students forget to dry their adipic acid. They add the thionyl chloride and the thionyl chloride just goes crazy, making a ton of sulfur dioxide gas. And they wonder why their reaction is taking so long. So we're going to oven dry our adipic acid to constant mass. We generally control the oven temperature to avoid decomposition. From here, we're going to characterize our adipic acid by measuring the mass, calculating the yield of product, taking an IR spectrum, melting point, and we're doing a chemical test for carboxylic acids, which is treatment with sodium hydrogen carbonate or sodium bicarbonate. Any acidic functional group, such as a carboxylic acid, will react with sodium hydrogen carbonate to produce carbon dioxide and the conjugate base. If we see bubbles when we mix our solid adipic acid and sodium hydrogen carbonate, that's a sign we have a carboxylic acid, and that's a sign that we have prepared the desired product. Does this discussion of how we're going to characterize our products make sense to everyone? Does everyone understand for the first part, the synthesis of adipic acid, how we're going to prepare the adipic acid, the mechanism for this reaction, and how we're going to characterize the adipic acid? Really pay attention to the IR spectra. We'll also take a proton NMR spectra as well. That's extra data, but I find the proton NMR is quite informative. In part B, we're reacting adipic acid with thionyl chloride to prepare adipoyl chloride. If your adipic acid is not dry, you're going to react and chew through a ton of your thionyl chloride. We use typically a large excess of thionyl chloride to help drive this reaction to completion. We've seen the mechanism before for conversion of a carboxylic acid to an acyl chloride with thionyl chloride. And what's important is the adipoyl chloride, we're not going to weigh out. We're going to keep it in the flask and we're going to use it as is. This is really important. This reaction is borderline quantitative. Generally, you get almost 100% yield of the acyl chloride product. So once we prepare our adipoyl chloride, we're going to characterize it via proton NMR, and we'll take an IR spectra and compare the carbonyl CO stretch in adipic acid and adipoyl chloride, as well as looking for the characteristic OH stretch for our carboxylic acid. What we'll notice is that, for example, if our adipoyl chloride shows up here and then our adipic acid shows here, the fact that we see a shift in the IR absorbance and the IR wave number value for our CO stretch, we're monitoring this CO stretch via IR to verify that the reaction has gone to completion. And that's why in the spectra that I provided you, I show an overlay between the adipic acid and adipoyl chloride spectra. So you can see that the reaction has gone to completion as our carbonyl CO stretch has shifted in wave number value. Does that make sense to everyone? Does that discussion make sense? Okay, in part C is really the for fun part, and you'll have to just watch the recording and sort of try to pretend that you were the person pulling the nylon if you were in person. Anyway, so what we'll do is we'll mix adipoyl chloride and hexane diamine to prepare nylon in the presence of catalytic sodium hydroxide. So this is a classic aminolysis reaction. And what's really cool about the reaction is it actually occurs at the surface interface. So we have our solution of our diamine, and we slowly add our adipoyl chloride along the side of the beaker. At the surface, nylon will form, and as we pull the strands off of the surface, the reaction is still polymerizing at the surface. So in real time, the nylon is polymerizing, and as we pull the strand off from the surface, the nylon continues to polymerize. And so you can pull these very long nylon strands. It didn't work that well when we pulled it. We just mostly ended up with a glob or some short strands. But usually when we run this as a class, we end up with a few really good batches where students can pull strands that are almost the length of the lab. And that's just because the nylon polymer contains tens of thousands of individual nylon units. So that's the nylon lab. It's a pretty straightforward lab, not a ton of data to analyze. And for the remainder of this lab period, what we'll be doing is working through the pre-lab for the nylon lab and continuing to work on our reports for the esterification lab and watching the video for the nylon lab so we can prepare our full report. So we'll archive this recording.